Welcome to the Wright Science Daily Revision Boost. In today's Biology Blast, we're going to be looking at natural selection and evolution. First thing we need to know is that evolution is a gradual change in a species over time. So this is something that takes a long time to actually occur. The way that organisms actually evolve is through the process of natural selection. And there are 5 key steps we need to remember for this. The first step is variation. So within a species, we've got variation there. And as mutations occur, that variation will increase. Step 2, survival of the fittest. This means that the organisms best adapted to their environment will survive, whereas those who are not well adapted will die. Step 3, reproduction. This is where those best adapted are more likely to survive to the age where they will reproduce, which leads on to step 4, passing on the advantage, where the genes from the parents are passed on to the offspring. So that means the offspring are more likely to have the same advantageous characteristics as their parents. And the last step is that it repeats, so that we see this repeating pattern of the first 4 sequences over many years, which will eventually lead to the development of a new species. We do need to know some examples of natural selection showing evolution, and the peppered moth is one. So before the 19th century, the majority of those peppered moths were light coloured and they camouflaged on the trees. However, the mutation for dark coloured moths made them more likely to be eaten by birds, so there were far fewer dark coloured moths than the light coloured ones. When the Industrial Revolution came about, then the trees became covered in soot, which meant that dark coloured moths were better camouflaged, and therefore the dark moths were more common in urban areas than light moths, so it was an advantage to be dark coloured. Second example is antibiotic resistance in bacteria. Now, bacteria evolve in a short time because they've got a very rapid rate of reproduction. We do find that certain mutations occur to make the bacteria resistant to antibiotics, and that will then be passed on to all offspring. So this can result in the whole species becoming resistant to an antibiotic, which is bad news for us as humans. We also have other evidence for evolution we need to be aware of. So we do have fossils that were formed when the remains of animals or plants became mineralized, which means they were changed into rocks, and we find older fossils buried deeper underground. So this means that those layers of fossils form a sequence showing how organisms have gradually changed over time. So that's what we refer to as the fossil record, which is that key piece of evidence for evolution. Some of our oldest rocks also contain fossilized bacteria, whereas more recent rocks contain fossils of more complex organisms. So this suggests that life on Earth evolved from bacteria originally. We also find plant fossils occurring before animal fossils, so it tells us that plants were needed before animals could evolve. We also use fossils to show that closely related organisms have evolved from the same ancestor. And a good example of this is the horse, which you can see at the bottom there, and the tiny little changes that happened between each version of the horse until we get to the modern day. Some other key points of evidence for evolution. We can use bacteria and Atlantic tomcod, which are a type of fish, in studying evolution because they've got very rapid reproduction rates. So this means that we can see how those changes happen in a much shorter space of time than, say, in humans. We can also carry out molecular comparison of DNA and the proteins of organisms, and what we find is that closely related species have most similar DNA and amino acid orders in their proteins. We also know that species that don't adapt to the environment will become extinct, and 99% of all species to have ever lived on Earth are now extinct. For those of you doing GCSE biology, you do need to know a little bit about the theory of evolution. So hopefully we know that before Darwin's work, people believed that all species were created by God. But in 1831, Darwin got on board the HMS Beagle and travelled all around the Galapagos Islands. And he'd read a book on geology by Lyell that suggested fossils were evidence of animals that lived millions of years ago. And what Darwin did on his voyage was he documented the different types of finches present on the islands, and what he realised was that the shape of the beak was linked into the food source on the island, and this was how he came up with his theory of natural selection. At the same time that Darwin was going around the Galapagos Islands, then we had Alfred Russel Wallace working in Borneo. And he sent his ideas to Darwin for peer review before he published his own theory of natural selection and evolution. Because their ideas were so similar, they presented the two papers jointly in 1858. Then in 1859, Darwin published On the Origin of Species, which introduced his ideas to non-scientists, so the general public, which is obviously one of those key ideas of publishing your work, is so that the general public also know. However, his book was very controversial at the time as it went against the teachings of the Bible. So there was a lot of mocking of Darwin, hence the old monkey cartoon that we see there that was used in the press. However, his theory is now widely accepted as we've got all of that evidence we've discussed that supports it. Last thing we're going to look at is the classification systems. So when we're talking about classification, this is sorting living organisms into groups based on their similar characteristics. And the reason that scientists will actually classify organisms is to identify species, to predict characteristics, and to show evolutionary links. When we're talking about that word species, we need to know the definition, which is a group of organisms which are able to reproduce to produce fertile offspring. So when we come to do this classification, then we start off with 7 taxonomic levels: kingdom, phylum, class, order, family, genus, species. You need to know the order of that, so find a little mnemonic that helps you remember it. We've got 5 kingdoms that all living things on Earth can be classified into: plants, animals, fungi, protoctista, and prokaryotes. So we've got a choice of 2 systems for classifying. First one, the artificial classification system, uses observable characteristics. So you'll just look at it and think, well, does it have wings, etc. It doesn't consider evolutionary relationships. The second type, the natural classification system, is based on evolutionary relationships which are determined through DNA analysis. And phylogeny is the study of evolutionary links through the study of DNA. Last thing to bear in mind is that when we're naming species, we use what's called a binomial system, bi meaning to, nomial name, and that comes from the genus and the species. Today's chemistry check is on rates of reaction. So when we're talking about the reaction rate, it's the measure of how quickly reactants are used or products are formed. And the way we work it out is the amount divided by time. When we've got an experiment that produces a gas and we're asked how we could measure the rate of it, one way is we can count bubbles, but that's not very accurate because the bubbles are all different sizes, so therefore have different volumes of gas, and it's highly likely to experience human error because you could miss some bubbles because they could be produced very quickly. So one way we could improve it is by using an upturned measuring cylinder that's filled with water, like the diagram on the left, because what we do there is we place the delivery tube underneath, and as the bubbles go up, it pushes the water out so we can read the volume off the measuring cylinder. If we wanted to be even more accurate, we could use a gas syringe, because that's on the right there and you can see all of the gas is collected, so there's no risk of the delivery tube falling out from under the measuring cylinder or losing a bit of water as you're upturning the measuring cylinder, etc. If they were to ask you to calculate the rate from a graph, then they could very well say calculate the rate between 60 and 90, for example. So you'd work out the difference in the time, the difference in the actual volume of gas, and then do your change in volume divided by the change in time. So it's the mean gradient we're calculating there. If they were to ask you to calculate the rate at a specific point, so what was the rate at 70 seconds, for example, then you'd need to do a tangent to the curve. So you put your ruler against the point on the curve you're investigating, adjust the angle of the ruler so it's an equal distance from the curve on each side of the point, draw your line using the ruler, and then make your right angle triangle to use the change in time and the change in volume just as we did previously. One of the common experiments that you'd have done with rates of reaction is using sodium thiosulfate and hydrochloric acid, because what happens there, you put some crosses on a piece of paper under the beaker, and then as it reacts, what you find is it goes cloudy and you can't see the crosses anymore. The first factor we need to consider is temperature. When we increase the temperature, the rate of reaction also increases. And the reason for this is that when the temperature increases, the particles gain kinetic energy. So that means they move faster and they will have more frequent successful collisions. Do remember when we're talking about the rate of reaction, it's inversely proportional to the reaction time. So that means 1 divided by time is directly proportional to the rate. Second factor to consider is concentration. When we're talking about the concentration, it's a measure of how much solute is dissolved in the solvent. And a more concentrated solution has a greater mass of solute dissolved in the same volume of solvent. When we increase the concentration, the rate of reaction also increases. And the reason for that is that in higher concentrations, the particles are more crowded, so they have more frequent collisions. What we do find though is that the reaction will stop when the limiting reactant has been used up. And on a graph you can tell where the reaction has stopped because the graph plateaus or goes horizontal. Do remember that the amount of product is proportional to the amount of limiting reactant. Third factor is pressure. If we increase the pressure, the particles become more crowded, so we get more frequent collisions and therefore the rate is faster. Our fourth factor is surface area. So when we break a material up into smaller pieces, the surface area increases. So our powders have a much larger surface area than a single lump of the same mass. When we increase the surface area, we increase the rate of reaction. The reason for this is that as the size of the lump decreases, the surface area to volume ratio increases. And this means that we've got more exposed particles, so there are more frequent collisions. The final way that we can change the rate of our reaction is by using a catalyst. So a catalyst is a substance that increases the rate of a reaction, but is unchanged at the end of the reaction. And catalysts are specific to a reaction. When we add a catalyst, then what happens is the rate of reaction increases. And the reason for that is that they provide an alternative reaction pathway that has a lower activation energy. So this means that a greater proportion of the colliding particles will reach the activation energy and therefore react. Today's physics prep is on radiation. So the first thing we look at is half-life. We should know that radiation is emitted at random. And to measure radiation, we use a device called a Geiger counter. So the Geiger counter measures the activity, and the activity is the radiation emitted per second, which is measured in becquerels. When we're talking about half-life, that's the time it takes for the activity to halve, or it could be described as the time it takes for half of the unstable nuclei to decay. Half-life could either be long or short depending on the material. So carbon-14 has a half-life of 5,700 years, but helium-6 has a half-life of 0.8 seconds. For those of you on the higher tier, you need to know how to calculate half-life. So if they give you a graph of activity over time, then look at the total activity on time 0, divide that by 2, then draw your horizontal line across from that number and then take it down to the x-axis and read off the value. The second way you can calculate half-life is by using calculations. So if we have a sample of radon-222 with an activity of 100 becquerels, calculate the activity after 11.4 days, the half-life of radon-222 is 3.8 days. First thing, calculate the number of half-lives. So 11.4 divided by 3.8 tells us it's 3, and then we calculate the new activity. We know each half-life reduces by half, so half times a half times a half gives us 1/8. 1/8 times 100, 12.5 is our answer. If we now consider the electron arrangement within atoms, we know that electrons occupy certain energy levels around the nucleus, and different atoms have different energy levels. The electrons will usually occupy the lowest possible energy level, so that's the smallest distance from the nucleus. In the photon model, electromagnetic radiation is emitted and absorbed as packets of energy called photons. The energy of each photon is proportional to its frequency. So in order to excite an electron to a higher energy level, a photon of the right energy must be absorbed. Once the photon has been absorbed, the electron moves to the higher energy level and the atom is then in an excited state. If we pass light of all frequencies through hydrogen gas, then some frequencies are absorbed. So we can create an absorption spectrum which shows the set of frequencies of radiation absorbed by an atom when excited electrons move to the higher energy levels, and you can see it at the bottom there. If a photon has enough energy, then it can completely remove an electron from the atom, and that means the atom is ionized. So photons of UV, X-ray and gamma ray frequencies have enough energy to ionize those atoms. When electrons move from a higher to lower energy level, then they emit radiation. And an emission spectrum shows a set of frequencies of radiation emitted by an atom when excited electrons move to a lower energy level, and you can see one at the bottom there. The frequency of radiation that's emitted depends on the difference in energy of the energy levels. So this energy change can take place in one go or in two or more. If it occurs over two or more, then the emitted photons will have less energy, lower frequencies and longer wavelengths. The largest energy difference we could see is from an energy level just below ionization, but that will vary in different atoms. So hydrogen can emit UV photons, but carbon can emit X-ray photons. Last thing to note is that protons and neutrons occupy energy levels in the nucleus and can emit gamma rays as the energy involved is much higher. Now we've had a quick recap, then head on over to socrative.com and test your knowledge on the topics from today. The room name you need to enter is Wright 2662. Good luck! As always, if there are topics that you're not 100% confident in, head on over to the playlists for the more detailed videos. So for biology it's B5, chemistry is C5, and physics for combined science is in the P4 playlist, and for the separate sciences it's in the P6 playlist.